Okay, so I want to discuss a relation between some very interesting numbers called the Bernoulli numbers and the Riemann zeta function. So the Bernoulli numbers are defined as follows. You have this function t over e to the t minus 1, and you can expand this as a Taylor series, and this is the sum of bn over n factorial t to the n. So this is the definition of the Bernoulli number. So you have this function, and from this you expand it, and you get these rational numbers. So the first few values look something like this. 1, 2, 3, 4, 5, 6, let's say. It looks like a half, 1/6, 0, negative 1 over 30, 0, 1 over 42. And then these numbers can get quite interesting. For example, the 12th Bernoulli number is negative 691 over 2,730. These may seem like random rational numbers, but these turn out to show up in a bunch of places. So the denominators, it turns out, are pretty easy to control, but the numerators are quite subtle and have surprising properties. So in number theory, these numerators, in fact, because of the relationship to the zeta function, control what is called the class group of cyclotomic extensions of Q. And another surprising place where they show up is in topology, where the numerators of the Bernoulli numbers control the sort of set of exotic spheres of certain dimensions. So these Bernoulli numbers are quite mysterious and surprising, to say the least. And one thing that you may have noticed is that every other number is 0. So if I put down 7, 7 would also be 0. And the reason is that this function is almost odd. If you like subtract off 2 over 2, then you can show that's an odd function. I don't want to do that, but this actually implies that, from what I'm about to write, the zeta function has zeros at negative even integers. So the relationship to discuss is that zeta of 1 minus n is equal to, I believe it is, negative bn over n. And here zeta is the beloved Riemann zeta function, which is the sum of 1 over n to the s for s greater than 1 and analytically continued to the rest of the complex plane. So I didn't appreciate this analytic continuation for quite a while, but it really is a subtle thing that you can extend this function to a unique function to the entire complex plane. So here, the extension, as you can see, necessary. This is for n natural number. And the extension is necessary because, well, we were evaluating at negative integers. So you've probably seen like some skeptical proofs of the sum of all natural numbers is negative 1/12. And what I wanted to do was understand this more general statement as to how you can get all the Bernoulli numbers out of it, because it seems like sort of an unexpected thing. So I'm going to do something that's even more skeptical than this expression, because it subsumes this expression by plugging in n equals 2, as we'll see. But sort of gives you an explanation as to why this is true. And also, I could state that using the reflection formula for zeta, if you know what that is, then using this method, which is going to be very skeptical mathematics, you can compute what zeta of n is for positive integers, for positive even integers at least, and then you can do things like the Basel problem or the sum of reciprocal fourth powers and so on and so forth. And then you can do some other things like sin to L functions, but there's a lot that you can say there. So what I want to present is somewhat underhanded mathematics, which will give an intuitive reason why this should be equal to this. And so this is not all formal mathematics. And if you don't like that, then I will say that at the end, using this reasoning, something interesting pops out, which is you get an expression for the zeta function that actually shows up in Riemann's paper, which I was always confused by. But it almost pops out very naturally if you try and make what I'm going to say in this video somewhat more rigorous. So without further ado, how do I get this expression that zeta of 1 minus n is equal to this? Well, so let's just start off by looking at zeta of minus s. So if we sort of pretend like this expression works for all s, then this should be equal to the sum of n to the s from n equals 1 to infinity. And what do we do with this? Well, there's a sort of nice little formula that I like, which is this. E to the d f of x is equal to f of x plus 1. And here by d, I mean df is equal to d by dx f of x. And so what I mean by this is that the left-hand side is the sum of 1 over n factorial d to the n times f of x. And so this d to the n times f of x really just means the nth derivative of f of x. That's the sum of f n of x over n factorial. And then this is the same thing as multiplying by 1 to the n. By Taylor's theorem, that's f of x plus 1. This is a really nice identity, intuitive to physicists, maybe less so to some mathematicians. But if you use this, then you can actually manipulate this expression a little bit and get a relationship with Bernoulli numbers at the end of it. You can kind of like see an e popping up here, and that's indeed the e that shows up over here. Okay, so what do we do with this? Well, what we can say is we can analyze the function x to the s, right? Let's call this function f of x. Let's fix s and look at this expression. And this is where things start to get a bit sketchy. So the first thing I'll say is that e to the d x to the s is equal to x plus 1 to the s. And in fact, you can do this procedure again. You can say e to the d times this is e to the d times x plus 1 to the s. That is equal to x plus 2 to the s, because x plus 1 plus 1. So in general, you can also combine this to say this is e to the 2d x to the s. And we can say that x plus n to the s is equal to e to the nd times x to the s, right? This is, again, you can use like the same sort of method over here to show this is just like follows from Taylor's theorem. Maybe this is like a formal notational thing, but turns out to be a powerful formal notational thing. So what we can say then is that the zeta of minus s, quote unquote, equals the sum of x plus n to the s evaluated at x equals 0, right? And here, for convenience, instead of starting from n equals 1, I'm going to start from n equals 0 to infinity. Since we're like taking s to be a positive number, and this should be, yeah, I guess I could say like s. I'm going to eventually take it to be a natural number. So if we're taking it to be a positive number, then there's no harm in adding n equals 0. It'll be more convenient for us later. So from this expression, we see that this is equal to the sum of e to the nd times x to the s evaluated at x equals 0, right, from n equals 0 to infinity. And now you can see that this guy does not depend on n at all. So we can just evaluate what this is going to be equal to. And you should recognize that that's just some sort of a geometric series. So it's 1 over 1 minus e to the d x to the s evaluated at x equals 0. So you can already start to see something that kind of looks like the Bernoulli numbers. Okay, so now you can actually just like do the next steps that I'm about to do with this function, and then you'll get like something similar except with the power series expansion of this. But in order to get the Bernoulli numbers as defined here, let's just modify this function to make it look more like this. So what I'm going to do is I'm going to add another d to this expression and look at what d over 1 minus e to the d is times x to the s evaluated at s equals 0. So this will be equal to d of, well, if we go back to this expression, x to the s plus x plus 1 to the s plus so on and so forth, evaluated at x equals 0, which is s times x to the s minus 1 plus x plus 1 to the s minus 1 plus so on and so forth, again at x equals 0. And this is just equal to s times 0 plus 1 to the s minus 1 plus 2 to the s minus 1, so on and so forth. So this is just equal to s times zeta of 1 minus s, right? Because this is negative s minus 1. So now you can actually basically already see that we're getting very, very close to this expression over here. And in fact, it's just a few short steps away. So now, if we expand this guy, in terms of the definition of the Bernoulli numbers, except we just replace the t here with the d, and then what we end up with is this is equal to the sum. The denominator has to be multiplied by a negative sign because here you have e to the t minus 1, here is 1 minus e to the d. This is negative b sub n over n factorial times, sorry, there should be a e to the n, and goes from 1 to infinity. And this gets, all of this expression gets multiplied by x to the s, so you get s equals 0. So all I've done is I've taken this power series expression and replaced t for d, and done that. And now, here is where we can actually, all of this is sort of skeptical, right? Because you're just like sort of formally manipulating infinite series all around. But here's where we get something really interesting. So this, it's like some infinite expression could not possibly converge. But what if we take s to be an integer that's greater than 0? So what happens then? Well, if we look at d to the n, x to the n, right? Well, this will be n times n minus 1 all the way up to n minus 1, or something like that, x to the power of n minus n, something like this. And if we evaluate this at x equals 0, then two things happen. One is, if n is greater than n, then what happens? Well, we're taking more derivatives than there is an exponent. So what happens there is that we get 0 because more derivatives than available. But also, n is less than n, then we see that we have leftover x, right? Because we have n minus n is greater than 0. And so when we plug in x equals 0, we also get 0. So the only contribution is when this n over here is equal to this exponent s, or I'm calling it big N. And what happens there? Well, when we take n derivatives of x to the n, we just get an n factorial. So that'll cancel out with that. And what we end up with is negative bn is equal to zeta 1 minus n times n. Or alternatively said, zeta of 1 minus n negative bn over n. So over here, for example, if you plug in n equals 2, then you get that zeta negative 1 is equal to, famously, negative, what would we have here, 1/6 over 2 is negative 1/12. Or if you wanted zeta of negative 3, well, that's equal to negative 1 over 30 over 4 equal to 1 over 120. So you can sort of get these expressions for, this should be like, for example, 1 cubed plus 2 cubed plus 3 cubed, and so on and so forth. And as I said, because these odd numbers are all 0, if you plug in even numbers for n, if you plug in odd numbers for n, you get that zeta of negative 2, negative 4, negative 6, and so on are all going to be 0, which tells you that the zeta function has roots at the negative even integers. So this is all a little bit skeptical, but ultimately, like, if you read a textbook and you look for a proof of this fact, it's ultimately this sort of an argument dressed up using some actual rigorous expression for the zeta function. So conversely, I'm going to say, let's say that we were like sort of playing around with functions and we came to this expression. Actually, in trying to make this a bit more formal, you can actually derive a really nice expression for the zeta function. So let's do that. So what we have just shown is that zeta of 1 minus s is equal to, quote unquote, d over 1 minus e to the d times x to the s evaluated at x equals 0. There should be an s up front as well. Okay. In fact, let's not use this expression. Let's actually use the other expression that we had a little bit earlier, which is zeta of s equals 1 over 1 minus e to the d x to the s evaluated at x equals 0. Okay? Looks like it's in the denominator. So how can we try and formalize this expression? This is sort of like an infinite series of some exponential of some derivative, which is kind of quite skeptical. And here at the end of the day, we're evaluating at x equals 0, which we saw as sort of the critical step to sort of get rid of a bunch of things. Well, one thing that we can do, in my opinion, this is the one trick of a good physicist, is take the Fourier transform. And what happens is, if we evaluate something at x equals 0, that's the same thing as the integral of the Fourier transform. Because the inverse Fourier transform is integrating the Fourier transform with respect to e to the power of I psi x, but evaluated at x equals 0, this just becomes 1. So what we can try and do is take the Fourier transform of this expression and then try and take the inverse Fourier transform and evaluate at x equals 0, which means just take the integral of that. And what we'll see is like we'll come up with some expression which looks like zeta of s. Okay, so let's do that. Well, what's the Fourier transform of 1 over 1 minus e to the d times x to the s? Well, this is the integral of e to the minus I psi x, x to the s, over 1 minus e to the d dx. Okay, so now, first, if you're well versed with Fourier transforms, you'll know that the derivative, once you take the Fourier transform, you can replace that with an I psi. This is equal to 1 over 1 minus e to the I psi, and I pulled out the integral because it doesn't depend on x anymore, times the integral. This should be from minus infinity to infinity, but I'm going to immediately ignore those bounds because I'm going to do something a little bit sketchy. E to the minus I psi x times x to the s dx. Now you can see that this kind of looks like an exponential of minus something times x to the s, so it almost looks like a gamma function. So we can sort of make it into a gamma function by rescaling and taking x to be x over I psi. And a convenient thing to do when you do a sort of rescaling like this is to multiply and divide by x, because once you do that, if you take x to x plus a, then dx doesn't change at all. Similarly, if you take x to ax, then dx over x doesn't change. And so what that means is that we can just plug this into here, and we get that this is equal to 1 over 1 minus e to the I psi times the integral of e to the minus x, and then plugging in x over I psi here, we have x to the s plus 1 over I psi, the s plus 1 dx over x. So now we can also pull this I psi over x plus 1 to the outside. We get is 1 over 1 minus e to the I psi times I psi power of negative 1 plus s times the integral of e to the minus x, x to the s plus 1 dx over x. And then this guy, by definition, is equal to gamma of 1 plus s, right? Okay, so now what we can do is we can take the inverse Fourier transform and integrate overall space instead of taking the actual full inverse Fourier transform, just the integrate overall space, which corresponds to the inverse Fourier transform at x equals 0. And then what we get is, let me replace s with minus s here. So we get zeta of s is equal to gamma of 1 minus s times 1 over 2 pi times the integral over all of space of I psi to the power of, here I place s with minus s, so I'll get s minus 1 over 1 minus e to the I psi d psi, right? And now, sort of, you want to change variables to get rid of the I. So you replace psi with psi over I. And this d psi will also get a 1 over I. This is equal to gamma 1 minus s. It's 1 over 2 pi I times the integral of psi to the s minus 1 over 1 minus e to the psi d psi. And in fact, 1 second, I'm checking the formula. Yeah, so Riemann's formula for the zeta function is that zeta of s is equal to negative gamma 1 minus s over 2 pi I times the integral of negative x to the power of s minus 1 over e to the x minus 1 dx over this contour c, where c is the contour that sort of goes from positive infinity near 0, wraps around 0 once, and then goes back around to positive infinity. So this appears in his paper on the primes less than a given magnitude. And you can see that, sort of just by these sort of arguments, maybe I missed a negative sign here or something. It might be that you actually get the exact same expression, but you get at least almost the same exact expression as Riemann. Here, the negative sign just, goes into flipping this around. But this sort of expression for the zeta function always seemed kind of mysterious to me. But if you just sort of take this sort of skeptical mathematics and you try and formalize it by taking a Fourier transform or inverse Fourier transform to make things converge, so to speak, then you actually get an explicit formula. And then this thing will converge, and then you can show that this agrees with the zeta function for positive s. And because everything here is well defined for all s, this can extend the zeta function to all values of s. So, and I think Riemann probably didn't just write this out of nowhere. He probably, I'm not saying he did exactly this, but he probably had some sort of a hand wavy thing that he came up with and said, okay, how can I formalize this? And then he came up with this. Now, one thing that I want to understand really well is how he came up with this contour. I think, coming up with complex integration counters, I think for certain things is sort of an art. Like if you know some quantum field theory, then the Feynman propagator has some special contour to take care of the poles, and that corresponds to like particles existing in negative and positive infinite time. So, but I mean, regardless, like this is some cute, sketchy math that you can apply to get some real mathematics at the end of the day, or at least an ansatz for some real mathematics. And one last thing before signing off is that here we have some relationship from the Bernoulli numbers to the sum of powers of all positive integers, right? Well, that's not defined, but we do have a well-defined notion of a sum of finite number of positive integers. So you can ask, can we come up with a formula for a sum of finite number of positive integers relating to the Bernoulli numbers? And it turns out that there is like an explicit formula that does that for you. So I'll probably do that in another video, and you can try and figure that out yourself if you want to.